All right.
Okay.
I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class. This time we have to meet together and study your creation. Help us to understand it, Lord. In your name I pray, Lord Jesus. Amen. All right. So today, I'm going to attempt to say something intelligent about the Frobenius theorem. So,
We won't notice if it's not.
what's that?
We probably won't notice if it's not intelligent. So
Oh,
it's okay.
sorry. I had. Well, anyway, there are bureaucratic issues that are distracting me. But here we go. So, as is often the case, this is actually probably the, what's it called? According to Rentelen, it's technically the Clepsch-Diana-Frobenius theorem. But Frobenius is usually the one who's named it, the Frobenius theorem. And the Frobenius theorem is a very interesting result that concerns sets of vector fields. All right. So let me just kind of tell you the big idea of it, which is, I mean, this is the question basically, is when does a set of vector fields on some manifold M align with a submanifold U at each. Well, that's not quite the right thing to say there. Submanifolds U, all right? I don't know. I think I have to give up on the intelligent part for today. But all right. So like the simplest case of this is the case of an integral curve. All right. So like we'll start there. Integral curve. All right. So suppose you have, a vector field. All right. And so we're talking about something like V is equal to a sum, I equals 1 to n of, let's say, V upper I, partial xi, right? So let me just suppose that that was disturbing. What even was that? Anyway, I think I somehow managed to step on the chair stopper. It sounded like it broke. Anyway, so we got a vector field, right? And we could talk about an integral curve. That would be something like, of course, V of gamma of t is equal to d gamma dt, right? That's the definition of integral curve, is that the tangent vector field to the curve aligns with the vector field in as much as, we're the applicability. Now, what that means then is that you have to solve the differential equation, Vi is equal to dxi dt for I equals 1 to n, yeah? So if we can solve this set of differential equations, that gives us the integral curve, right? Let me be more specific. So, example 1, we might have the vector field V is something like, x partial x minus y partial y, all right? Something like that. And if we want to find integral curves, we're up against the following differential equation. We got to solve dx dt equals to x, and we got to solve dy dt equals to minus y, all right? I think we can do that, right? Calc 2. Calculus 2. Separate, integrate, right? If you've had differential equations, just write down the answers. Did I just hear no fair? It's true. It's not fair. Some people know more than others. Let's see here. So yeah, x of t is equal to x naught times e to the t, and y of t equals to y naught e to the minus t, right? In particular, we could define gamma, gamma of t is equal to, x naught e to the t, y naught e to the minus t. There you go. This is an integral curve that goes through the point x naught, y naught for this, right? Now, I think we could actually do even better for this one. Can you guys find the Cartesian equation? Maybe we can visualize this better even. Can you eliminate t for me? Let me show you a trick. You want to find the Cartesian equation, check this out. dy dt divided by dx dt is dy dx. But that's also minus y over x, which is giving me dy over y equals to minus dx over x. Natural log of the absolute value of y is equal to minus the natural log of the absolute value of x plus a constant. So we get y is equal to a constant divided by x. Or I think that, wait, hold on a second. Yeah. Yeah. So, all right. I guess what's going on then, right, is we have right. Right. I mean, if you think about it, you pick any point, right? There's an integral curve through that point, right? And so this is actually the lowest order example of the Frobenius theorem in some sense. The vector field has integral submanifolds. In this case, they're curves. They're one-dimensional manifolds, right? Every curve is a one-dimensional manifold. And if you look at it, I think, ignoring the well, I bet the coordinate axes are also integral curves, aren't they? Those are maybe special ones. There's something funny going on the x and y axes. Are those also integral curves? What do you guys think? See, this one set x naught equals to 0 and set y naught equals to e to the minus t. Well, I guess we can either do, well, fine, y naught e to the minus t. I guess we could stick with that. Could I just do,
No, I mean, just go with y with something.
oh, just y equal to y?
Why not? Why not? It's a constant. That's our question.
So, oh, y is equal to, how about y is equal, maybe would y equals to t work, maybe? I don't know. In other words, if I put gamma of t equal to, say, 0t, is that an integral curve? If I calculate, gamma prime, I have just partial y, right? Yeah, I don't think that works. I need to have that. I need to have that. Well, I can. Good gracious. y naught e to the minus t, I suppose, right? And then when I do that, this gives me minus y naught, right, e to the minus t times partial y, which is minus y partial y, I think. Right? And then it's hard to see it, but notice that there's also plus x partial x here as well, right? Now keep in mind that, I mean, to be somewhat, I mean, clear is probably too strong a word, but what I really mean to say is that both of these guys, these are at gamma of t, all right? Right. I mean, to be fussy, when I solve dx dt equals to x, what I'm really solving is d dt of x composed with gamma is equal to x composed with gamma of t, and d of y composed with gamma is equal to y composed with gamma of t. I'm solving for respectively the first and second components of the integral curve. It's just, rather than coming up with new names for these, we just use x and y for them again in the interest of confusing the students. Mission accomplished. So, yeah, so in short, I think you're right. I think this is an integral curve. Yeah. And if I put the y naught here, that just makes time 0, you know, like wherever that is. And where does it go? As time goes to infinity, it goes to like that, right? Well, if we run time negative, right, it goes up here, right? So like this would be t going to minus infinity. And this is down here, t goes to infinity. Oh, you're right, it doesn't reach the origin, does it? Yeah. Approaches it. And I think there's a similar story to be told for the x-axis, right? We probably can find, I have a suspicion, we can find integral curves over there that they approach the origin but don't quite get there. Oh, that's true, but it won't change the fate of the integral curve. It won't change the fate of the integral curve. Like, we're still going to end up all the way up and not quite reaching the origin. Of course, if you... Oh, yeah, down, exactly. So, similar story down here, exactly. Yeah, thank you. We either go up or we go down. But yeah. Okay, anyway, so this is an integral curve, all right? And in fact, we can define a flow using this integral curve. What I mean to say is, like, if you pick a point in the plane, right? If I pick a point in the plane, then I can kind of like go along these curves using this. I'm trying to think of how to remember my notation. Hey, let me go on. Let me not do that. Maybe my brain will loosen as we go on. Okay, so so what if we had like two vector fields? If we had two vector fields, then maybe we could think about whether or not they align with like some surface in the manifold. All right. So I need to give you guys a definition. A k-dimensional distribution and we use triangle for this, of manifold is a smooth assignment of a k-dimensional, goodness gracious, k-dimensional subspace, let's say triangle P of TPM at each point point P and M. All right. If you're keeping score, I'm in Appendix F. All right. So page 284 of Rentlin. Now, so the smoothness of the condition is equivalent to saying that every point Q in some neighborhood of P we can write, so to smoothness is equivalent to saying that, it turns out that it's equivalent to saying that there exists a set of smooth vector fields that at any point you can write as the span. So like the smoothness, what it amounts to in terms of us is to say that, well, this is actually, I'll use a Q, the span of x1 of Q, x2 of Q, xk of Q, all right? So, let me read it again here. At every point Q in some neighborhood of P, delta sub Q is generated by k linearly independent vector fields. So this is for all Q in some neighborhood of P, right? And we can do this for every point. For every point in the manifold, we can pick a set of k vector fields that the span of those vector fields will match the distribution, all right? Will match this subspace in the neighborhood of the point. Is there a question or no? Oh, you spelled for all wrong. No.
F-O-R-A-L, no space.
Huh. Interesting. Not sure what to say about that. So definition, the distribution is integrable all right, if for each P in M there exists a submanifold, all right, sigma containing P, all right, such that the tangent space to Q at sigma is equal to the distribution at Q for all Q in sigma. In other words, the tangent spaces to sigma all lie in the distribution. All right. The submanifold sigma is called an integral submanifold of delta. So this is a integral submanifold of delta. All right. So as I was just saying, integral curves are the first example of this. They're a vector field is a one-dimensional distribution, right? Or at least it corresponds directly to a one-dimensional distribution. I suppose, okay, fine. Technically speaking, a vector field is not a one-dimensional distribution, right? A one-dimensional distribution is a selection of a tangent line, like a whole line of tangents. It's a subspace of the tangent space, right? So, like, to be fussy, a one-dimensional distribution is not just a vector at the point. It is the vector and all scalar multiples of it, right? But if you have a non-vanishing vector field, obviously this corresponds to a one-dimensional distribution in the sense that the vector field at the point will give you a basis for that one-dimensional distribution, you know? So, like if I could hazard a picture, and this might be dangerous, if this is my space, right? And up here I'll just write all possible tangent spaces vertically, right? So like if I pick a point here, I could kind of visualize the tangent space like this up here or something, you know? And I have another point over here. Something like that, you know. A one-dimensional distribution would be essentially just picking a line in each one of these tangent spaces. You know, it'd be like, it's here, right? Maybe it's over here, like that one, you know? But a vector field, right? X. Oops. I've been trying to use V today. Let's stick with that. If we look at that, that's just something like this, right? Okay. So, something like that.
Can we just attach any subspace you want to it, or does it have to be the subspace that's the derivation of the manifold at that point?
Well, a distribution is a selection of a subspace for the tangent space. What was your question?
So the distribution is necessary, like the distribution at one point is necessarily contained in the tangent space.
Right, yes. But it's not just one tangent space, right? It's thinking about all tangent spaces collectively. So it's a smooth assignment of a subspace. Whatever that means, because we certainly haven't defined that notion of smoothness in here. But Rentelen comes out and says, oh, and by the way, what that means for us is that at any point you can write the distribution as a span of linearly independent vectors, right? They're pointwise linearly independent for each Q in the neighborhood, you know? So, so then the question then, of course, is like, okay, great. If we have this, you know, distribution, right? What condition do you need for it to be integrable? That's the question then, right? Like, if I have a distribution, when is it going to be the case that it's integrable? Is every distribution like this? You know? And it turns out no, not all distributions are integrable. There are other distributions which will not align with submanifolds in a systematic way, like an integrable one will. So, and I have an example we'll look at of that. But that brings us to our next definition. Which is to say that the distribution is involutive. All right, involutive if for all P and M, and this is funny. See, this, like, the funny thing is, like, if you listen to me talk about distributions any other day, I'll say a distribution is a set of vector fields, you know? Like that's my default thinking, right? Am I wrong, Preston? If you don't remember? All right. Shane, do you remember?
Nope.
No? Rats. So, but you notice he shifts here from saying it's a smooth assignment of a k-dimensional subspace to talking about the generating vector fields. Right? So, I mean, the smooth assignment of a subspace is kind of an ethereal idea, given a set of vector fields, that's something a little bit more tangible for us, right? So essentially that's going to be going forward, we're going to think of a distribution in terms of the vector fields which generate it. All right? The tricky thing is that's a local idea. It might not be possible to have the same set of vector fields generate the distribution over the totality of the manifold. You might need to change up your generating vector fields at different locales, right? So that's probably what's stopping us from just saying, assume it's a set of vector fields, period. Yeah.
That make it not smooth.
Well, sometimes we can only go so far. You know, like you can't find a coordinate chart for the whole sphere. You can find a coordinate chart for part of the sphere. It's that kind of thing.
So they still match each other on the edges.
Yeah, something like that. So it's involutive if for all p and for all I and j less than k, we have the Lie bracket of x sub I of q with x sub j of q is an element of the distribution at q. This is what it means to be involutive. It's closed under its Lie algebra. Well, excuse me, the Lie bracket of the vector fields closes back on itself. Like schematically, we're saying that delta bracket delta is a subset of delta, right? So that's like schematically, there's a quick summary of what I'm saying. If we take two things in the distribution and we calculate the Lie bracket, we get back to something in the distribution again. What's that? Yeah, I think that, well, we can say things about that, but I will behave. Okay, so for example, if we had a set of commuting vector fields, that would be a involutive distribution, right? Like, because if you have commuting vector fields, the Lie bracket's 0, right? In which case, yay, 0 is always in the subspace, so yeah, so like let's give a specific but perhaps too stupid example. Two stupid examples are good though. Example 2. We can think about our manifold being R3, right? And we can think about the distribution being generated. And despite my comments about the inability to globally generate, I rescind those comments for this because, we can do this. All right? This is a distribution. What am I saying? I'm saying that, if I take the tangent space to R3, I can, look at the horizontal vectors, yeah? And that's a two-dimensional subspace, which, by the way, will align with these, right? Like, so let's see here, how can I say this? Sigma, what's sigma in this case? Through the point, let's say, let's say through P1, P2, P3. What would this specifically be? Can you tell me the submanifold? I'll start you out. There you go. How about this? X, Y, and X and Y, or whatever you like. So like, okay, so what are the integral curves to partial X? we are looking for dx dt equals to 1 and dy dt equals to 0. How about 2 partial y? There we got ourselves dy dt equals to 1 and dx dt equals to 0. So my integral curve, I'll call it 1 of t, would just be, I guess x naught plus t, comma y naught. Gamma 2. My integral curve to partial y is going to be x naught, and I think y naught plus t will do it. And instead of using a t, let me use an s for a change of pace. Right? So if you could envision, that was supposed to be horizontal. I tried. Here, let me fix it. There we go. Now it's clearly horizontal. All right. Here's y, here's x, here's z. Nothing to see here. All right. So I'm talking about if we pick, a point here, p naught equal to x naught, y naught, z naught, I guess, is my current language. Then the integral curves through that are just this, right? That's like my, oh, my bad. Oh, come on, guys, don't let me do this. These are three-dimensional vector fields, right? So I owe you something else, which is what? Yeah, the third component, right? Whoa, it's like everything's three-dimensional. Like one of those movies, and all of a sudden, your whole field of vision is a third dimension. Flatland, okay. I've not seen that actually, but I believe it. Kind of sad, isn't it? I haven't seen that. But anyway, I'm always busy when you guys have the movie night. So I'm just saying that these integral curves lie in the z equals z naught plane, right? In fact, they lie in a plane of constant. This one lies in a plane of constant y and z. This one lies in a plane of constant x and z. But they both lie in a plane of constant z. They both lie in the plane z equals z naught, right? So like this is my gamma 1, and the gamma 2 is the other guy. So essentially, you can use the integral curves to the given vector fields, and you can flow along those curves, and they're going to trace out a potential direction in what you'd like to be an integral submanifold. And it just so happens if the vector fields commute, right? And by the way, it's a straightforward calculation to work out that partial x, partial y. If we do that on f, we're talking about partial squared f, partial x, partial y, minus partial squared f, partial y, partial x, which is 0. So therefore, the bracket of these is 0, right? This is a general result. If we're talking about coordinate derivations, they commute. Coordinate derivations commute. So what that means, though, if we study the concept of flow, it turns out that if you flow along the integral curves of vector fields, something like this happens. you might flow along one direction, and then another direction, and then another direction, and then another direction. Like if I have two vector fields, so suppose I had a vector field V and a vector field W, and let me do some color coding. So like maybe these are both like flows along V. Something like that. I'm fuzzy on this idea right now. I'm sorry, guys. I wish I wasn't. But this piece right here, it turns out it has to do with the commutator of V and W. If you study the flow correctly, there's this concept of a flow box, and if you want to flow along the V direction and along the W direction, and then vice versa, flow. It's supposed to be V. Oh yeah. So flow along the. So here I'm saying flow along the V curve and then flow along the W curve for the upper path, right? And then flow along the W curve and then flow along the V curve for the second path. Those would be equivalent journeys following the integral curves of V and W only if the commutator is 0. And so like you can kind of see that down here. If I start at a point and I flow along, the integral curve of partial x, partial y, and then I flow along the integral curve of like partial the other ones. Like there's more. I just drew it at one point, but you see there's these everywhere, right? And so if you think about it, if you were to flow from one point, right, and if you were to flow first the green, then the blue, or if you were to flow the green, then the green, flow the blue, then the green, you'd get to the same point. The reason you get to the same point, actually, is because the vector fields commute. All right? So if that's the case, what we can basically do is we can use the integral curves and weave them together and build a surface. This is sort of the most naive case, in some sense. If the vector fields are commuting, you can just build a surface using sort of the union of the integral curves appropriately so. I'm being obviously a little bit fuzzy here, but this illustrates the idea. What's interesting is that even when they're not commuting, it's enough that the commutator of the vector fields is in the same ballpark. Like if it's a sum of these two things. Like for example, if I somehow had a vector field V1 and a vector field V2, right? And if I had the commutator of V1 and V2 was equal to like V1 plus V2, this would tell me that my, this thing is involutive. But this thing I'm sketching about creating the integral submanifold, it wouldn't work out quite so simple, because when I did this, I wouldn't when I flowed along the V integral curve and the V1 integral curve, and I flowed along the V2 integral curve, I wouldn't end up back in the same spot. But the thing that displaces them is based on just a sum of the vectors, which means that the integral curve to this thing, if you can imagine it, is still in the same plane that's generated by the original two integral curves in some sense, all right? Anyway, let me go on. So well, do you have an example that's not just coordinate derivations? Well, yes, we do. Let me show you. I need to go to Walmart and buy some markers. We're fresh out of markers in the department. It is a sad situation. Oh, I wasn't trying to complain about you.
I don't have the authority. Yeah, it's not like you can just buy stuff for that money. I have no access to the math department's money.
Yeah, well, I guess you're just like the math department then.
Oh, dang.
Let's see here. All right. Okay, so this is the example that everybody goes to. It's the standard example of a vector, a distribution which is not involutive. All right. And so it's probably instructive to go through this example. All right, so here it is. We have a vector field x equal to partial x plus z partial y, and we have y is equal to partial z. All right. If we calculate the Lie bracket of these, right, we'll let that act on f. We got what? We got partial x plus z partial y on partial z of f minus partial z of partial x plus z partial y acting on f. So this gives us partial x partial zf plus z partial y partial zf minus partial z partial xf, then product rule. So I get minus partial yf minus z partial yf. All right. Oh well. And if you look at that, what's that? Oh, it just come apart. So this and that, they be canceling because the partial derivatives commute. And likewise, this term and that term, they cancel as those partial derivatives commute. And we're just left with minus partial yf. So therefore, since f is an arbitrary test function, we have that the Lie bracket of x and y is simply equal to minus partial y. All right. So then, the question then is, if we wanted, so suppose, so then the Ratlin's like, suppose it is integrable, and let sigma be the integral surface through the origin, right? Suppose towards a contradiction. That, so this collectively is delta. Delta is integrable. And sigma is integral submanifold. All right. Through the origin. This is the specific one through the origin. All right. So containing 0. All right. So if we draw a picture, we can visualize what x and y look like at the origin, and we can just kind of like, maybe that's helpful. What does x look like at the origin? Well, z is equal to 0 there, right? So that means that x just looks like essentially this. Yeah? That's x at the origin. It looks like that. What's y look like at the origin? So we can visualize it like this, right? So that means that by the way, the integral curves to any vector field in your distribution must fall in the integral submanifold. Does that make sense? I think it makes sense. So that means that, like the z-axis, right, and the x-axis, these guys, they need to lie in sigma, yeah? But he says the integral curves of x are obtained from the equations blah. Let's see here. So let's look at that. So let's see here. You guys tell me, what differential equation would we be trying to solve? Are we trying to solve dx dt equals to what? 1? From that, dy dt is equal to 0. Oh, my bad. Dy dt equal to what? Z. All right, good. And dz dt equals to 0. So this is for the integral curves to x. All right. And he points out that the solution to this looks like x of t, y of t, z of t equal to t plus a, ct plus b, and c for some constants a, b, and c. Well, they're linked.
Oh, I see. Okay.
See, so I mean, you can see if you believe it or not. I mean, so dz dt is a constant, right? So once you know that that's a constant, then that constant goes here. Well, dy dt is equal to a constant. Integrate. You've got a constant times t plus another constant b. But then dx dt is 1, so that means x is equal to t plus a constant, which we're calling a. All right. So this calculation right here doesn't have anything to do directly with the origin, right? That's just the integral curves to x. But now we can find the integral curve to x that goes through the origin, right? So if we want to go through the origin, what do we need to do? I think we have to put a equals to b equals to c equals to 0 to go through 0, 0, 0, right? At least at time 0, right? So I guess the, let's see here. I'm trying to, well, fine. He says, this means that sigma contains an open subset of the x-axis. Right? An open subset of the x-axis. All right. I mean, I guess if I put b equals to 0 and c equals to 0, t plus a is free to range, right? So I don't know. But then he says, but the integral curves of y all contain what? I mean, something like gamma of t is what? Like x naught, y naught, and z naught plus t, right? He says, so sigma must contain a small area of the xz plane. All right. did I miss? Yeah?
According to the first, the x of t, y of t, z of t, that definition of the integral curves, if y varies in the vertical direction, it also varies in the y direction. Like, if it varies in the y direction, it varies in the vertical direction, vice versa. So it can't travel just along the z-axis.
Oh yeah, so that, like you're saying that the integral curves of x have to do, I mean, they might look like this right at the origin, but they've got some kind of like this sense to them. In my picture, I can't do it, but they're, like you said, they're going in the y direction here as well, right?
Y and z are the difference.
Well, the x and the y, right? Like,
Oh, yeah.
the x and y are linked. I guess it's in a constant z, but it's moving the x and y. So like, I don't know, if I if I could formulate the argument better, the point is, if we study this carefully, we're flowing in the x and the y direction thanks to the integral curves of x. But if we focus our attention, on the other hand, y, we're flowing in the z direction. But this is all happening right at the point 0. If you can, on a two-dimensional surface, flow in the z direction and the x direction and the y direction, we're not talking about a two-dimensional surface, right? You've got 3 linearly independent tangent vectors to this allegedly two-dimensional integral surface. You can't have this, right? So it's always challenging for me to visualize the reason for this. I've seen a lot of different pictures in a lot of different books, and I still haven't drawn the picture for myself that I really get it, you know? But here's, well, that's not the picture. Sorry, guys. Let's see if there's a picture in, maybe a picture in Lee. Yeah. If you look at page 492 here, you guys can pass it around. This gives you some sense of, I think, the picture. Oh, man. Oh, yeah, that's it. This, you can draw some picture like that. Might be helpful. I don't know. But, okay, so now that I have almost given you a counterexample, let us go on here. So the Frobenius theorem, if I can state it eventually, what does it say? So this is the theorem. The distribution triangle is completely integrable if and only if it is involutive. All right. In other words, we can find integral submanifolds to a given set of vector fields only if it's the case that those vector fields, when we take the Lie brackets of them, the Lie bracket ends up again being just a linear combination of those vector fields again. This is what has to happen. Yeah.
What does it mean to be completely integrable?
Good question. By definition, a k-dimensional distribution is completely integrable if it's integrable, and for each p, yeah, okay, it's a stronger thing. Thank you. That is a very good question, because that actually gives us a license to something a little bit more, which is to say that it's actually the span of a set of coordinate vector derivations. So to say that it's completely integrable means that for each p there's a neighborhood u and local coordinates x1 through xn, such that everywhere the distribution is given by the span of the coordinate derivations for the first k coordinates. All right. So this is what completely integral means, that, in fact, the distribution is such that you can pick a local coordinate system. And with respect to that system of local coordinates, you can use the coordinate derivations of the first k coordinates to build the distribution.
That's not just any coordinate system.
No, there exists a coordinate system. So, like, this was the stupid idea behind my example over there. I actually used the coordinate derivations to build a distribution, and basically what happened there is the integral submanifolds are simply set the remaining variables equal to a constant. Those are your integral submanifolds. You know, like, we could easily extend that example. So, like, example 4, I guess. So if we're in, like, say Rn, right, and I let nabla equal to the span of, you know, partial 1, partial 2, partial k, right? This is a k-dimensional distribution, and the integral submanifolds are simply what? Thank you very much. J equal to what? Bigger than k, right? So J equals k plus 1 all the way out to n. So that would make this a k-dimensional submanifold, because we're freezing out n minus k parameters, and we're just letting the first k Cartesian variables be the parameters. It's a generalization of my previous stupid example. But the Frobenius theorem says that it's actually possible for an involutive distribution, all right, to pick a coordinate system that makes it look like this. It's possible to choose local coordinates where your integral submanifolds simply become constant coordinate solutions, right? Now, these integral submanifolds are often called leaves in a foliation. Leaves in a foliation, the idea is simply that they will fill out the whole space. And you can see that here, right? Like, if you let these constants vary, right? What you have, if I could draw a picture, right? Oh, I'm sorry. Then there's a stack of these integral, submanifolds. There's a stack of them. One for each, there was something happened to my axis along the way here somewhere. Don't look at it, it's hideous. All right. All right. So, like, there's a stack of these integral vector field, integral submanifolds to this distribution, and they fill out all of Rn.